Hey, what's up, guys? Welcome to my YouTube channel. So in this video, I'm going to talking about this interesting problem in the advanced calculus. So basically, you ask, is there a function having a limit at every point while being nowhere continuous? Okay, and hopefully it's understandable that what these are saying. Okay. Okay. So right. So in the advanced calculus, there are some weird function, right? So probably the first function f, where it's basically there is this function where it's a nowhere continuous, and then this is easy to construct, right? You just did f of x to be, let's say x belong to rational number is 1, irrational number is 0. This is the Dirichlet function, right? So you know that rational number is dense in a real number, right? So so this f is nowhere continuous. And there is also a function where it's nowhere differentiable. Right, but continuous. Okay, so basically this means that there is a function which every point are continuous but nowhere differentiable. Okay, then the question arises, right? Question arises. You want to ask some more difficult question. You want to ask where there is a function, let's say f from real number to real number, such that the first one is that f is it has limits at all real number, but f is nowhere continuous. Okay, so basically what it's saying is that you can always approach a f of x, but this guy is always different from f of a for every a, so real number. And you want to ask whether you can construct such a weird function which is nowhere continuous, but it always has a limit. Okay. And the answer is no. Okay. And then this is actually some exercise in the routines homework or exercise. And but I'm gonna show a different approach. Okay. So proof. And the idea is simple, right? So you define a g of x to be the limit. Let's say y approach to x, f of x. Okay. And right, so g of y. Okay, so g is a function, right? And the g is different from f. Okay. So the first thing you need to claim is that g is continuous. This is important. Okay. The goal is to first prove g is continuous. And the reason is the following, right? So let's say you want to prove g is continuous. Basically, you want to say that if if 2 points, let's say a and b, right? If let's say a and b are close enough, then g of a and g of b are close enough, right? This is the definition epsilon delta. Okay, so by definition, you know that let's say we pick limit to be a. Okay, so let's say we consider this equation. Okay, so this equation tell you something. Tell you that if you are close enough to delta, then your f of x will differ from g of a by at most epsilon. Okay. Now you can pick x to be very close to a. Okay. So let's say you pick x very close to a, but x is b. Okay, you pick x to be b. Because on b where b is very close to a. Okay. Okay, but notice something, right? So you have g of a minus epsilon, f of b, g of a plus epsilon, right? But notice something, right? No, but notice something. Notice that limit x to b, f of x will become g of b, right? Right. So it means that when you're when your x is close to b, now I can pick x to be a, right? I can pick x to be a. Okay, so where a is close to b, when your a is close to b, then your f of a, when your x is close to b, right? Then your f of a will close to g of b. Okay, your f of a will close to g of b. Okay, so this means something, right? This means that right. So okay, so you pick x to be b. So that means that when b minus a is small enough, then g of a minus epsilon is less than f of b, right? The plus g of a plus epsilon. Okay, but let's say if you take if you take x, okay, maybe let me just don't write this equation. If you take x to be close to b, as I say a and b, right? Now if you there are these delta, right? If you pick some points where it's close approach to b, okay, then this guy is still in this region. Okay, so it means that if you take limit x to b from this equation from both sides, then you get g of a minus epsilon. That's then limit x goes to b, right? So you become g of b, g of a plus epsilon, right? So it means that when a, b are close enough, then g of b is close to g of a, right? So this means that g of a minus g of b is less than epsilon. So this shows that g is continuous. Well, maybe this is not a good reason, but if you take a limit from both sides, then you get this. Okay. Okay, so since g is continuous, then we are able to prove the theorem. Well, we were able to prove the function does not exist. So now you can define h of x to be f minus g. Okay, so notice, so okay, so g is continuous, right? So limit x belongs to a. For every a, h of x exists. And it's continuous, right? It's continuous, right? So continuous means that limit x goes to a, g of x will just be g of a. But by definition, g of a is limit x goes to a, f of x. Okay. Okay, so notice that this is g of a by definition is different from f of a, but this is well defined. Okay, so limit x goes to h of x exists, and is equal to 0, right? By this equation. Okay. Okay. So now let's consider the particular interval, 0, 1 interval. So h is a function, h is a continuous function. Sorry, no continuous, h has limit 0. Okay. For all x belongs to interval. Okay. So and I want to claim that let's say this is condition. H has a limit equals 0 for all x belongs to interval. I want to claim that the discontinuity point of h is finite. Okay, so the number of discontinuity, is countable. It's countable. If I show this is true, that means that the function does not exist, because by definition, this function should have, if f is nowhere differentiable, nowhere continuous, then it should have uncountable points, right? But I will show that the number of discontinuous points is at most countable. Okay, so the reason is the following. So you consider the closed interval, right? So now you can define a set. Let's call it a an to be the x belongs to interval such that the absolute value of h of x greater than 1 over n. Okay, and the discontinuity points, right? So the discontinuity point A will just be the union of A. Or I can just define A to be this. Okay. And okay. All right, so this is the definition. Okay, so then what I want to say is that okay, so I want to say that let's say I take an. Okay, so for every n, my claim is that an is finite. Okay, the reason is that the reason is the following: if an is infinite on an interval I, that means that by Weierstrass theorem, right, there is the accumulation point. Accumulation point means that you can find the points which any closed every small in any small interval will contain infinite point in I. Okay, let's call this point C. Then you can take limit x goes to C, right? Because this is accumulation points, so I can take this limit, right? H of x, right? But by definition, if I take this, then it should be 0 by the definition of h of x. But now this is impossible, right? Because h of x has absolute value 1 over n for any fixed n. So this is a contradiction. Okay, so it means that an must be finite. Okay, since an must be finite, so a must be countable. A can only be countable. And all the discontinuity points will just captured by A. Okay, by definition. So all these discontinuity points will captured by A. Okay, so A is and can be only be countable. Okay, so that's it. So this is the proof. And yeah, see you guys next videos.